Okay, well this is calculus. This is 7.3, the third part. This is called the shell method for finding volumes. You might wonder why we need three different methods, and partly is because the AP people decided this year to teach all three methods, but there's actually a real valuable reason for using the third method, and I'll get to that in a second. Let me try and explain what the shell method does. When we're trying to find a volume, we need an area which we are then rotating in some way, or an area where we know what the shape is. If I was to take this paper and say I want to find the volume of it, what we did is we said, well, let's take this distance, if we were taking this area, and we'll just rotate it, revolve it around. And then because as x changes, goes from 0, say, to whatever this number is, that distance gets larger as we go across. But imagine that we wanted to do something different. And this is what the shell method does. What it does is it takes that, I don't know if you can see that well, and it says, what if I was to take this little area and simply think of that little section, almost like a piece of an onion, a shell out of the onion. Maybe we could just rotate it around. And that is called the shell. Now you say, well, how does that help? Well, it helps because this, and let me hold it up here, I've cut it. I don't know if you can see it, but that's a rectangle. It has a, we'll call this the length. This is the width, this little section, and we'll call this the height. Now I've tried to stretch it out straight, but you get the idea. This is a large rectangle which was made from this. So let me give an example. Let's say that we wanted the area between y is square root of x, y equals 0, x equals 4, and we want to revolve it around the y-axis. And you may say, well, why the y-axis? Just trust me, it'll be easier. So we have this, okay? If I take and think of this slot here, and I'm going to exaggerate this. It's normally not this big. This is my dx. This is my, we'll call this the width. And this is the length. And then this, like I showed you then, is this, which then goes back. And this we'll call the height. Well, the height is how far we're revolving around the y-axis, how far this is being revolved. And so in this case, our height is, this length right here is x, but actually that x is the radius, and the length of it is 2 pi r. It's the distance around the circle. So this x gives me, in a sense, the radius of rotation. This is going to revolve around like this. And as a result, the volume here will be the length times the width times the height. The length is this distance from here to here, and in this case, that would be square root of x minus 0. That would be our length. Our height is 2 pi r, but in this case, r is how far we are from our axis of rotation, which would be x, and our width would be dx. And all we have to do to get to the answer is to integrate from 4 to 0, x, square root of x, dx, and put the 2 pi out in front. And I did that for us to save time. That's 128 pi over 5. Now you might say, well, what happens if you go around the x-axis? If you go on around the x-axis, you're going to have to do the same thing we did before, in that we're going to have to switch everything around. In other words, I would need to take this y is equal to square root of x, rewrite it x is square root of y then is x squared. This point right here, it's not drawn real well, is 4, 2. So we would have to switch it from x equals 4, y equal 2 to x equals 2, y is equal to 4. And this line, which was y is equal to 0, becomes x equal 0. And if I then redid all of that, what I would get is this region here being revolved around the x-axis, excuse me, it's this region here being revolved around the x-axis. And now we could put our, remember we're trying to do this with the shell method, there's my shell. Wait a minute, no, this is between. So it actually would be like this. Let's see, I'm having trouble with this. It would be, yeah, it would be this right here, and it would now be being revolved around. And what we would get is pi, 2 pi from 2 to 0, from 2, and x times x squared dx. Okay, kind of a pain to do it that way. What you're going to find is it's real easy to do volumes with the shell method around the y-axis. In fact, so much that we ought to do them every time that we can, actually. So let me show you a few more problems. I'm not going to work them as problems. We'll have time tomorrow, and each day you can call and get office hours, but let me show you another problem. We'll make this more general. Imagine that we had these two. This is y1 and y2. Well, let's make y2 on top, y1 and y2. Let's say I wanted to revolve this around the y-axis. Well, how would I do that? I'd find these points of intersection, A to B. I would figure out what my disk is, not my disk, excuse me, what my length is. Remember, it's always length times width times height. The width is my dx. The height is how far it's being revolved. It's this distance here. So that would be my radius. And in this case, that would be 2 pi times r, which would be 2 pi times x. In other words, if you tell me what x is, I'll tell you how far away this is. And the length here would be y2 minus y1. And so this would be 2 pi from B to A, x times y2 minus y1 dx. And that's all you would have to do and you would get to the answer. What makes it more interesting, perhaps, is what happens if we're revolving around some other line. For instance, let's say that we were revolving it around this line, y is equal to c. Well, then in that case, this doesn't change, and this doesn't change, but my height is going to change. My height is the distance of rotation. So let's just choose a spot. I'm going to move this one over. Let's choose this. How far away is that? Well, this distance right here is x. This is c. This distance is x minus c. And so this would be x minus c, and we would have 2 pi from B to A, or A to B, x minus c, y2 minus y1 dx. Right? If this had been on the other side, so let's get rid of this, and let's put it over here, well then in that case, the distance of revolution would be x plus c, and you would have 2 pi from B to A, x plus c, y2 minus y1 dx. What you're going to find is that whenever you have to revolve around the y-axis or a vertical rotation, this shell method is just so simple to use. If you're going around an x-axis or a horizontal rotation of any sort, this actually is more difficult to use because, like we showed over here, you actually have to redo the whole thing and think of it as something different that's being revolved. We have to change our axes, change the y's for x's, and so on. Okay. All right, it looks like I'm cutting out, so I'm going to end the video at that point.